I wanted to tell you about case analysis, which is a powerful tool for proving theorems by breaking it into several cases and tackling each case separately. It's a surprisingly simple way of attacking the problem, but it's often very useful. So far, the two strategies we've had for proving things have been direct proofs, just following the definitions, or proof by contradiction. So for this example, I'm going to prove a theorem that says the absolute value of x times y is always equal to the absolute value of x times the absolute value of y for all x, y real numbers. And remember, what is the absolute value sign? Well, the absolute value of a is equal to a if a is greater than or equal to 0, and the absolute value of a is equal to minus a if a is less than 0. Remember that definition. So let's break this up into cases. Case 1. X is greater than or equal to 0, and y is greater than or equal to 0. In this case, the absolute value of x times y just equals x times y, and the absolute value of x equals x, and the absolute value of y equals y. Everything's positive. So that proved the theorem for the case when x is greater than or equal to 0 and y is greater than or equal to 0. Okay, case 2, x is less than 0 and y is greater than or equal to 0. Okay, in this case, x times y is going to be the negation of, I should say, the absolute value of x times y is going to be minus x times y. But remember, x is less than 0 here, so minus x is actually equal to the absolute value of x. Y is positive, so that's equal to the absolute value of y. In case 3, we have x is greater than or equal to 0 and y is less than 0. In this case, we have the absolute value of x times y, again, will be minus x times y. This is equal to x times minus y. And x, remember x is positive, are greater than or equal to 0, so x is the absolute value of x, and y is less than 0, so minus y is equal to the absolute value of y. So again, we have the equality that we wanted. I guess I should write little equal signs in here. And finally, case 4, x is less than 0 and y is less than 0. In this case, x, the absolute value of x times y, is going to be, well, it's going to be minus x times minus y. And this is equal to, again, the absolute value of x times the absolute value of y. So in all 4 cases, we were able to prove the theorem, and each case was relatively simple. Notice that case 2 and case 3 were nearly identical. In case 2, x is less than 0 and y is greater than or equal to 0. In case 3, x is greater than or equal to 0 and y is less than 0. But the arguments are the same. We could have grouped these 2 cases together. By that I mean we could have simply had a case, let's say 2 star, that grouped these 2 cases together, and case 2 star would have said, assume exactly one of x, y are negative. Right? Case 2 handles the case when x is negative, case 3 handles the case when y is negative, but we could have grouped these together and said, hey, here's a case 2 star. Assume exactly one of x and y are negative. And usually when we do this, we say something, we say without loss of generality, assume x is negative. Or I guess we could have also said, without loss of generality, assume that y is negative. What this without loss of generality means is, hey, I actually have 2 cases here, but they're identical. Since they're identical, let's just assume that y is negative. And the case when x is negative is identical. Or if you had assumed x is negative, you would have said, oh, well, let's just assume x is negative. The other case is identical. So if you hear me say without loss of generality in class, it means that I'm combining a few cases, but there's really only one we need to look at because the others are the same. Let me do another example of a proof that uses case analysis, and I'll mention without loss of generality, and it also works by contradiction, so it's good practice for that. So the example is actually example 7 in the Rosen book from section 1.8, and it says if x and y are integers where x times y and x plus y are even, then both x and y are even. So if you have two integers where x times y is even and x plus y is even, then both x and y are even. So let's do a proof by contradiction. And we'll assume that it's false. So assume that it's not the case that x and y are even. Okay, well if it's not the case that x and y are even, then what cases do we have to consider? Well, we have the case where x, that means, x is odd and y is even. X is even and y is even. Sorry, y is odd. And x is odd and y is odd. Since this is a proof by contradiction, I need to show that each one of these three cases leads to a contradiction. Now it turns out that these two cases are going to be nearly identical. So without loss of generality, I'm going to assume that x is odd, because the x is even case and y is odd case is the same as the x is odd case and y is even case. So I'm just going to do this one. You can see they're sort of symmetric cases. And then that'll leave us with this case here to take care of. But you'll see that in both of these cases x is odd. So without loss of generality, let's assume that x is odd. Like I said, we have to show that both of these cases lead to a contradiction. So in this case, where x is odd and y is even, we have an odd plus an even. This is going to equal something that's odd. And that contradicts the fact that x plus y is even. That's what we initially assumed. In this case, we have x is odd and y is odd. This implies that x times y is odd. An odd number times an odd number gives you an odd number. Well, if x times y is odd, that contradicts the fact that we assumed that x times y was even. So again, in this case, where x is odd and y is even, we contradicted the fact that we assumed that x plus y was even. And in this case, x is odd and y is odd, we get x times y is odd. That contradicts the fact that x times y we assumed was even. Now, again, we left out this case here, but it's because it's identical to this case. So we were able to assume without loss of generality that x was always odd. And this completes the proof.